We're now going to introduce the logic that expresses the properties of the transition system that we are interested in. It is called computation tree logic, abbreviated CTL. And in this section we are going to introduce the components by example. So let us recall the transition system we looked at before, the one that had the state A as initial state and transitions back and forth between A and E, transition from E down to H, and back and forth between G and H. And let's recall the labeling function, labeling A and E to be vowels and G and H to be consonants, abbreviated V and C. An atomic proposition holds in a state if and only if the labeling function for the state contains the atomic proposition. In the example on the right, we write E models V to indicate that in the state E, the property V holds. In general, what is to the left of this model symbol is the state var sigma, and what is to the right is a formula phi in the logic we are looking at. Next, let us go on to reachability in one step. The property EX tells about what is possible to reach taking just one step. Again, if we look at the state E, it is possible in one step to go to a state that satisfies the property C. Namely, we go from E to H, and H satisfies the property C. Another formula is AX of phi, saying that regardless of which path we are taking, starting in the current state, does phi hold in the next state. In the example on the right, starting from the state A, regardless of which path we are taking, in fact there is only one, we will be having E as the next state, and the property V of being a vowel does hold there. Now it is time to try it out for yourself. The formula AX of EX of C, does that hold in the state A? The formula EX of AX of C, does that hold in the state A? We now move on from reachability in one step to what is reachable in many steps. The first formula we look at is EF of phi. It talks about whether it is possible in a number of steps, possibly 0, to move from the state we are looking at to a state that satisfies phi. In the example that we are looking at on the right, the state A satisfies a property that it is possible to move from A to a state that satisfies C. Namely, we can go from A to E to H, and H is satisfying C. On the other hand, from the state G, the property EF of V does not hold because there is no way we can go from G back to one of the states A or E where V is holding. Another formula is AF of phi, talking about whether for all paths leaving the current state that there is a state on that path that satisfies the property phi. In the example on the right, in the state G, we have the property AF of C because the state G is in fact on every path leaving G, and the state G satisfies the property C of being a consonant. On the other hand, from the state A, the property AF of C does not hold because there is a path going AE, 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 and so on, where none of the states on this path satisfy the property C of being a consonant. These formulae that we're looking at can be combined using the usual logical conjunctions like negation, conjunction, disjunction, implication, and so on and so forth. So now is the time for you to take a look at these new formulae and look at the state A. Is it the case that AF of EX of C holds? Is it the case that EF of AF of V holds? And is it the case that EF of not AF of V holds? We now move on to unavoidability. The first formula is EG of phi. It talks about whether in the state we are, is it possible to find a path where phi holds on every state on that path. In the example on the right, in the state A, EG of V holds because I can choose the path AE, 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 and both of the two states on that path satisfy the property V of being a vowel. Another formula is AG of phi, talking about all the paths that leave the current state. will it be the case that all the states on such a path satisfies the property phi? In the example on the right, looking at the state G, the property AG of C does hold because the only path we can actually choose leaving G is the one GH, and every state on that path satisfies the property C of being a consonant. That's a lot of new concepts just in one go, so let's briefly summarize at the bottom what we've been looking at. There are two ways of choosing the path. E, for can we find a path that lives up to our expectations? And A, will our expectations be satisfied by all paths starting this point regardless of which one we were thinking of choosing? And then we have the next letter in our formula, the X, for what is possible in just one step, and the F for what is possible in 0 or more steps, and for the G, what must be possible for each and every state on that particular path. Well, it's time to try it out. On the small example on the right, AX EG of C does hold an A, similarly for EX of AG of C, and for AG of non-EX of V. Finally, for a somewhat larger example, let's look at the towers of Hanoi once again. Looking at the state at the top, where all the disks are on the rod A, does there exist a path where in the next step all the disks are on the rod C? Is it the case for all paths that in the next step all the disks are on the rod C? And also try these formulae on reachability in 0 or more steps and about unavoidability. Once you've done this, you should read the section in the book doing the try-it-outs on the way.